My name is Andreea Lita, and I recently graduated from a master in automation and robotics, but I have the background in aerospace engineering. So as you can see, very big on the screen, it's the ISAE Supaero logo, and this is because I had the opportunity to do an Erasmus on my last year of master. So this is also where I had the chance to work on a very practical thesis, as I was involved in a student team, which was doing its first iterations for a competition that I will discuss quickly on. But the main idea was, how can we get to discover an early risk management for this model-based approach we want to have for a complex system, which in our case was a rover and a drone. So this is just the 7 parts I will be going through the next 20 minutes. And just to explain a bit the background on which this work has been developed. So here in Europe, we have the opportunity to participate in the European Rover Challenge. As a definition, it's just an international robotics competition. Why is it super interesting is that it's happening in such way and in such conditions that replicates the Mars conditions and gives you a lot of tasks that challenge you from a technical point of view. So the idea is, you have this Mars yard in Krakow in Poland, and a lot of students within the entire Europe, actually multiple universities per country, apply. They apply for this type of competition. And based on the rule book, you usually receive, as the timeline on the right presents, during around February, when you are creating your proposal based on the rules, they give you all the information you need in order to actually create this complex system of a rover and a drone that need to work together. Of course, everybody puts a bit more accent on the rover, because he is the one doing all the science task navigation, in the sense of, maybe you have a task to retrieve a certain type of soil that is colored at 30 centimeters depth within the Martian ground, and you need to reach until the 30 centimeter line to get the pink type of Martian soil. So you need a drill. How do you connect the drill? How do you do the interfaces and the electrical part? How do you connect everything? So it's a lot of technicalities that give you the opportunity to push yourself into learning the technical parts that usually you do not always have access within the school you're doing. So for me, learning about space systems, automation, robotics, this was the best place to learn and to grow more onto my technical capabilities. So beside the tasks and beside the timeline, we can see that this is not an entire 1 year. You start somewhere in February, and then you should be having everything done by September. So it's quite a lot of work put in the second part of your school year. So for us, quickly it became clear that we need to focus on reliability. And just to make sure we are all on the same page, for us, reliability is the ability to perform without failure in certain conditions. So we have the conditions from the competition, and we want to be able to perform without having any problems. Therefore, our approach was to do multiple iterations until we got the opportunity to see the rule book. So technically speaking, we started slow. As you can see on the left, there is Celine, our very first prototype. It's completely 3D printed, an Arduino inside, nothing much. But then we started growing into looking onto either competitions or possibilities to test our knowledge and to prepare ourselves for the competition itself. But we quickly realized that through each iteration, reliability problems are rarely only just one bug. They come from interfaces, assumptions, missing links. We need reliability. We also need traceability. And that is very easily linked with all the problems we discovered during the work. Because for us, we were a first iteration. We never participated into this competition before. The student team just happened to start its existence a year before I joined. So there was not a lot of information to be shared. But nonetheless, for people who had work experience, as I was lucky enough to have before doing my Erasmus, it was difficult to have scattered information, like to share also the information that we knew from before, but also to keep everything in one place. There were high stakes because everything is costly, and we had a very novice team. So we thought of why should we look into a model-based approach. Like, our big why was because this was a real mission, we had a competition, and we wanted to kill every late surprises in terms of performance. And then the small why is that we wanted to help with the information not being scattered anymore. Like, people rotate every semester. This happens all the time. This doesn't happen in a company as often, but usually decisions and logics behind some of the decisions are lost. And so we try to find a common solution within all of those. So in the beginning, as it was way easier for us, we received the rules. We started with a lot of spreadsheets, a lot of Word documents, presentations. And in the end, we succeeded through all of this, which was a terror, to be honest, to do a preliminary design report. But we also found in the meantime, as at Supaero, we had the opportunity to discuss with experts during classes. I think somebody from Thales mentioned to us about MBSE, and they just show us a bit about Capella. But then when we looked into it and we saw, oh, we really have this very logical architecture that makes us ask the good questions, the right questions, and especially for a young team that doesn't have the knowledge and the experience to know what even to ask, this was a game changer. So I've discussed about this approach with my teachers as well, with my mentors at Supaero, and they were very happy to let me work on this research question on how can a lightweight MBSE workflow boost the system reliability versus the documents approach that we already tried for the preliminary design review. So we clearly stated the approach. We knew that the students needed this, but we needed a pilot site in the sense of it was easy to explain, oh, MBSE would be so good for us, but in practice, not having something clear to show the students and to explain that this is going to be so easy. We're going to have a model. Everybody's going to have access. Everybody can do this traceability so easily. We're going to have a component. You can see the requirements, maybe the test that needs to be done, maybe documents linked with it. And so because we were also time pressured, we want to have a clear deliverables in the end and to see what can we get out of this approach. So we had a mission on actually going and delivering a good system for the European Rover Challenge, a system that is capable of doing all these tasks, which were intense. As you can see on the right, actually, you can see a rover and the drone. The drone usually, just to make a clear idea, the drone should go around the Martian terrain, and they have some images, like patterns they need to see, and then they have this map that they created virtually, and they send it to the rover, and the rover should autonomously do all the tasks. He should know that he should go in this area. As you can see in the image, for example, there is a panel, should have the capability to go switch some of the things, flip a button, push something, grab something else, grab maybe a stone from the Martian terrain, put it in the back, have a scale in the back, measure the pH. The idea is that the competition gave us a lot of possibility to learn. And just a quick look with what we succeeded on doing. For me, this slide is a physical reality check. For us, it was a fast iteration, and this is where reliability issues show up brutally. Cable power distribution wasn't clear. Also unclear responsibilities. People didn't know what type of interfaces they needed to have with the other subsystems. Actually, the drone, this is the last picture before the drone has been bumped to the ground, because we didn't have a proper meeting to discuss the procedure on how to test the drone properly before flying it for the first time. So yeah, but this is why, especially, we wanted to focus on the idea of a lightweight MBSE model. And because I already got hooked up in Capella and we actually scattered the market, we looked for the possibilities to see, is there any other, I don't know, software that can get us the opportunity to work with, like, license for students, or give us references or just recommendations on where to look, what to do. And Capella also comes with its own example. Like, they have an integrated example that you can go and do your own reverse engineering. Like, you can go click, mess around, actually see, because the interface is quite friendly, but again, it's a new interface. So it takes you the time to accommodate, and having already something done with a logic that you can follow, it's way easier. So as you can see, Capella has a lot of things, and the Arcadia methodology is super good because it gives you the right starting point for somebody who doesn't have enough experience, at least work experience, which is almost everybody's case during student competition preparations. So we looked at these 4 layers, and we wanted to make sure that the path that we follow really follows this viewpoint. So we have operational needs, and we look into our rule book. Then we need, what are the system functions? What does it need to do? And we have the tasks. Then what would be a logical design? And in the end, what is the actual physical component allocation? This is it. Everything else can come after we manage to create this lightweight model, in which we can also present to the students that everything is clear and the logic is approachable even for somebody that never used it or like opened it before. All right. I'm sorry. So for the operational analysis, this actually helps us understand who interacts with whom, like what is in the environment, what are the outcomes of the mission. And now I know first time seeing a diagram like this may be something that makes us look a bit, like stay a bit in the back and see, looks quite complicated. But we actually tried to ask ourselves, after reading the rule book, which is also a complicated document, everybody has complicated documents, and actually putting them in diagrams is what makes them digestible. This was at least our logic. We have the actors that we need to work with. We have the places we need to work with those type of actors. And then we did scenarios, which are the ones like the color lines. What is connected with which? We simply wanted through this type of diagrams to look where ambiguity lied and to make it very visible, especially in the early design, especially when we still had time before the critical design review. So we could still change things. And we wanted to see, do we have missing actors, missing exchanges, unclear responsibilities? So in reliability terms, we just wanted to make sure we can describe this operational interactions, all of us, in the same way without arguing about what is the mission objective. It is actually something I like very much, because it's simply just a model mission process. Like, this had no reference before. This was just us playing with Capella. It was the very beginning. It was just, oh, can we put this picture here? Can we link a test? Can we link risks? And of course, Capella has a lot of nice add-ons. We haven't used them. I see they exist. You can link requirements and tests. So this, again, is something we want to implement for the future. But for us, it was nice to see that visually we can help people, and especially subsystems, make sure we're all on the same page. Because we woke up in some of the moments while preparing the design where subsystems between each other, they didn't know what type of data do they need to be transmitted, or what type of interface do they have one with the other. So again, it was simply mess around and finding out. So it was a good practice. Otherwise, we couldn't have seen some of the errors that we caught before CDR, but I would arrive there as well. So going to the second layer would be system analysis. So this just translates the stakeholder goals. What is the purpose of this? What functions does the system need to do? Not as colored, maybe a bit more complicated, but we wanted, I remember we spit it a bit through because we wanted to have this model as clear as possible, or at least to a readable iteration before the CDR. So we really looked into how to make this as comprehensive as possible, just to make sure we caught the risks early. So we needed to make sure that functions trace back to mission needs. And this is where traceability won, in the sense, because we prevented orphan functions to not have capabilities associated. Then logical architecture. We need to group those functions into logical components to define the data control exchanges, to make sure that the interface risks shows up early without having us integrated something that we don't know the protocol, or with what bandwidth do we need to discuss. And of course, we could go even in more depth than what we wrote in this type of diagrams, of course. But for us, it was good to just sit in a meeting, all of us, and say, okay, me as the system engineer of this project, I have no idea how to connect, I don't know, the robotic arm with the the thermal management system, there is anything through them. No, thermal management system should be by itself. Maybe with the mobility system should have some connections. What are these connections? Can we discuss with the subsystems? So even without the automation, just making the interfaces explicit helped the team conversation to change from, we assume that is this, to actually discuss in the moment and make the decision, which wouldn't be the case if we would have had multiple spreadsheets across different platforms, which happened in the beginning before the PDR. And the last one, the physical architecture, it's just you allocate the logical components to the real hardware. We were lucky enough to have the possibility to actually have the hardware before, so some of the hardware at least. And we looked into how this rover, drone, ground station were connecting, and including power or communications path, or just to make sure we spot any integration risks before integration was happening. And for us, this translated into some of the time savings and some of the lessons learned, in the sense of that time savings. We realized that we can detect earlier some of the gaps, especially with the hardware, as we realized not everybody read maybe the specs, or it was just before the hardware freeze, it was easily understandable, more easy to understand actually than previously, the links between one another. Also, we had the shorter decision cycles. As I said, it was a very real example. We just stayed in one room, we have this model, we click on it, we play with it, we move it around, but it's visual, and we can say, okay, we have all of this, how do we make it work together? But of course, that doesn't always would be the easiest way. Maybe we'll find even more iteration, and in the future we'll show you. But for us, it really helped in this case, in comparison with what we had before. And then rapid onboarding, this is especially something we want to test this year, but this is how we want to present what we did last year, how we want to do more. And the minutes, not evenings, is just that it was easier to discuss on this visual thing rather than going through all the documentation. Yeah, and lessons learned. Yes, tight schedules, like weekly student meetings leave not much time for new tool chains to approach. So it was me working on this pilot model. I couldn't get the others to work with me as well. We discussed about it. They agreed if I want to put in the work. And I think it was worth it, because now I know that, because it's February, they received the second rule book they ever had, and they will start again. So we will have a discussion very in the beginning. I will present them the methodology, the possibilities, and they can have people working from the beginning, not after they got used to where all the things are to move them around. So tooling is not always the option. We came with the tooling, but we needed to make sure they also have a mentor that helps them understand, especially when students also stay 8 hours a day as well at work, and then they still need to take the time for something they're passionate about. And conclusions. Well, we definitely learned that Capella workflow gave a real risk and trace visibility for us. This is something clear. And then that we replace the scattered spreadsheets and documentation. This is again something I hope it will be the case for this year as well. Maybe not for all the documentation, of course. They are not that advanced, but I think we can arrive there. And yeah, the fact that this was a contribution to show also that Capella can really help in terms of a student level team, and that Arcadia is a methodology that I think it's applicable for all the, let's say, young, I forgot the right term, but the engineers that don't yet have all the experience and that still want to help within the teams they are in. I think it's a good place to start, to make sure you have this idea of this recipe of early defect detection evidence and transferable templates for future. So for us, for Supaero Moon, this was an amazing project for me as well. I was very happy to work to it. I'm very happy to share my model with the next iteration. And yeah, I think that's pretty much it. Thank you very much for your time. And if you have any questions, I think I am in time, so it's good. Yeah.
Okay, thank you very much for this presentation, Andreea. That was really, really interesting. I think we have one question for you. So, what do you mean by lightweight approach? Is it simplicity? How does this relate to project management, such as Agile PM?
Well, lightweight is definitely in the simplicity we worked with. As I mentioned, Capella has a lot of functionalities we didn't approach because we were very time constrained. So we simply looked into what is the basic of a model that can get us to this model-based system approach as beginners, as someone who didn't have that into curriculum. We are not taught in schools about MBSE, even though I find it important. Maybe some people, if they do, I think some of the people at Supaero, if they did the system engineering specialty, but other than that, for me, it was simply just mentioned once, and then I realized how much it would have helped us. So yeah, with the lightweight approach, simply the simplicity that we could use, because we divided Capella into the only 4 layers we focused on working. And then the relation with project management, it was mostly, as a project manager, you also need to make sure people who come new get on board, they have a proper training. Well, student teams in this case don't really have the time. And of course, they have the problem of missing of sharing the information. Like the people who leave the student team, the association, they don't always do this sharing of knowledge with the people who are coming. So creating a model that has everything together and it's, let's say, interactive in the sense that they can open it, they can click on it, they can see the requirements linked, the tests, everything. It's very good for them. As for Agile, again, this was, I think, mentioned once for us. We didn't necessarily approach it. So for Agile project management, I wouldn't know how to say, but for project management itself, I do see a relation and I do see a benefit of using an MBSE approach, and like Capella, especially if the organization is a beginner in this sense.
All right, thank you. Great presentation, Andreea. How do you plan on comparing the 2 approaches, document-based and model-based, and how do you quantify the results?
The quantifying of the results comes from how many problems have we identified with this model. And the example that I had was, as I said, the fact that some of the teams never thought of discussing. Everybody assumed we know. And I wouldn't have known how to ask if I wouldn't have had the methodology and the layers. And I wasn't put, oh, I have this task of creating this diagram. This diagram is done in this way. I need to ask the teams about it. And they figured it out that they didn't know. And for me, in the thesis, I have an entire table in which I wrote what things have we discovered during this time. Yeah. And it's quantifiable as well because we now have a model that can be used and improved with every iteration. Not only documents, copy paste, see what the other said. If so, usually all documentation is not properly read or just when needed. I see it quantifiable because we ended up with clear results of the help and with a model, interactive model that can be used in future iterations.
We'll move to the next presentation. So thank you very much, Andreea, for your presentation. That was great. And so now I will put, thank you very much. Next speakers, so Kaylee and Aruk.
Okay, so Sydney Interplanetary Rover Initiative, SIRI, envisages a sustainable, diverse and thriving space industry for the next generation. That's our vision. And at SIRI, we aim to develop a modular rover that's capable of undertaking missions for both lunar and Martian terrain. So in this case, the Australian Rover Challenge and the University Rover Challenge that's in the States. We are also committed to leverage advanced system engineering methodologies that That's why we choose MBSE, Model-Based System Engineering, to achieve digitization and also to embrace the mission complexity. And beyond technical innovation, SIRI do place a very strong emphasis on outreach and inclusivity. So we volunteer a lot with the Department of Education in Australia and at a lot of the local events. So we do strive to make the space ecosystem more accessible for everyone who's interested in space, but also for the general public to foster a better community and engagement. So many of us, if not all of us, must have had experience working on the complex systems, collaborating with multidisciplinary teams and colleagues. And aerospace and space robotic is such an area with high attention to details, along with precise planning from the beginning. So why do we need system engineering at SIRI? Well, of course, is to better align ourselves with our stakeholders, with our sponsors, with our supporters, and also to manage the complexity, to reduce the risk, to improve the quality and control the cost so we can deliver the project on time, on budget. So our motivation, the biggest motivation for us is, so if big companies can use MBSE, why can not a student team use MBSE, for example, or a smaller company? So we want to prove that, and then also to showcase smaller teams like student teams with around 50 students, we can do just the same. So here we will be looking at the feasibility of implementing MBSE in a student-led rover team. So for context, the SIRI team, myself, I'm the project lead. This is our structure. We have the technical team, we have the operation team. Within our technical team, we have different subsystems. We have the robotic arm, electrical, software, structures, and science team. And then within operations, we have admin and logistics, we got finance and marketing. So now we're going into the Australian Rover Challenge. That's the main mission competition we'll be going for this year. The Australian Rover Challenge composed of 4 major tasks. The first one is post-landing task, where you can imagine the lander just landed on the moon and the rover have to go out of the lander. And we'll be also moving on to the excavation and construction task, where the rover will be supporting the astronaut to do construction of a lunar base. There's also the science resources task. We'll be looking at whether there's ice water on the surface of the moon. And lastly, there is the mapping and autonomous mission, where the rover will go autonomously on the surface of the simulated lunar terrain to map the terrain and then explore basically the arena. So within this presentation, we'll have a major focus on the post-landing task. The post-landing task, as you can see on the screen here, it does incorporate the rover just landing on the moon and going down the lander. And after that, it requires system check and ensuring the lander is not too faulty. So this is where the rover will be conducting a series of maintenance tasks. It will also navigate to relay status readouts to ensure the communication between the lander and the base station works perfectly. And it will also perform a series of processing jobs, for example, propellant hose connections, typing on keyboard, flicking switches, using controllers, things like that. And of course, the rover itself will also map the arena to understand what the terrain looks like.
Thank you, Kaylee. So having gone through the Australian Rover Challenge tasks, the rest of the presentation will now run through how we've modeled this in Capella, specifically for the post-landing task of the competition. So we all know the Arcadia method, the 4-phase method of operation analysis all the way through the physical architecture. So I'm going to walk you through how we've modeled in each of these phases. In each phase, I'll take you through our iterations of our models, as well as what changes we made in our iterations through the lessons that we learned. Starting with operation analysis, our idea of operation analysis is what the user of the system needs to accomplish. So it's viewing the system from a user perspective. And keeping this in mind, we didn't get off to a really good start at the beginning because we modeled something that didn't really help us in designing the rover. We modeled mission planning and preparation related content in Capella, but it did not really benefit us in designing the rover, particularly to complete the task that we intended. So therefore, we had to take a step back. We had to go back and think, okay, who are our operational actors for this project? We know we have a rover system that automatically becomes one of our operational actors, and we know we need to have an operator to operate the rover, becomes another actor. And to bridge these two actors, the rover system and the operator, we need a base station system, which becomes our third operational actor. Each of them have their basic functionalities, operational functions that they will be performing. So for the operator, that is as simple as operating the rover, which is through manual commands that goes through the base station, which converts these manual commands to operational signals that then gets relayed to the rover system through wireless signal, which then performs those tasks. Now, once the rover performs these tasks, it needs to give some feedback through the base station back to the operator. So both the base station system and the rover system now has to have two-way communication capabilities. And once this data is received, the operator then interprets this data, this feedback, and then makes operator decisions based on this information that was received. So our operational analysis, our operational architecture diagram looks as simple as that. And taking this, we then transition this into the system analysis layer, where we take a different perspective of the system. Now we think, okay, what does the system need to accomplish for the user? Remember, operational analysis was thinking from the user's perspective, and now we are moving into a system perspective. And from here, we started modeling what functions our rover system, our intended solution system, must perform. And one of the biggest mistakes we made here is that at the time we thought we were modeling functions that our system would perform. However, our functions that we modeled were actually a series of tasks. They were scenarios comprising of series of tasks rather than specific tasks that our system would perform. So in this case, it became a scenario diagram rather than a dependency diagram that should have been modeled in this phase. In addition, when we were modeling for different functions that the system should have, we noticed that some of the system functions were repeated in different functional chains, so, which is not a correct modeling practice. We should have one unique function for each task that the system must perform. So that was one of our mistakes we identified in our first iteration. Taking these and trying to fix this in our second iteration, this is one of our, to show our working diagram, trying to eliminate some of the repeated functions that we had in our system architecture diagram. And these functional chains that you can see, the colored lines connecting some of the functions, grouping some of the functions, are based on some of the tasks that we have to perform as part of the post-landing activity. So once we cleaned the diagram, once we eliminated some of the repeated functions, we then arrived at our third iteration, which we revised all the functions because, as I mentioned previously, we were modeling scenarios and not actual functions that the rover can perform. For example, in the previous diagram, you can notice there's a function called over here, function called move to the front of the lander. Now, move to the front of the lander is a scenario which is performed through a series of tasks, right? So when breaking down moving to the lander into minute detailed tasks that the rover can perform, we arrived at this diagram, which breaks down specific components of actions that the rover system will perform. And we also, you can note that we mapped it to the same operational actors that we identified at the start of our project. So already we are seeing some example of traceability in our project. So this being our final iteration from the system analysis layer, we now move on to what we call the logical architecture. So we transitioned all these functions in the logical architecture. And here we see how does the system work to fulfill the expectations that are the system functions defined in the previous step. So in our first iteration, we mentioned that some of the functions were modeled as scenarios. That was still the case in this iteration, which had to be fixed in the next step. But in addition to that, we identified some subsystems that our rover system will have. Even though this is a correct step in modeling, what we made a mistake in was in Capella, we modeled them as logical actors rather than logical components, which had to be corrected in the next step. So moving on to the next iteration, we then cleaned all our functions, eliminated all the repeated functions, and correctly modeled all the subsystems as logical components. And you can see a clean, simplified diagram where every function is a unique task that the rover will perform, and every function is now connected between each other, showing their functional exchanges. Now, one of the benefits of this diagram that we realized as a team is that this showed us how the different subsystems interact with each other for us as a team. So when we modeled and showed this to the rest of the team, our larger team was able to understand, they knew how their subsystem functioned, but this gave them an idea of how the other subsystems came together in operation. So that was one of the biggest advantages. But when we looked at this, we still realized that there were still some pieces and some functions that were missing in our process. Therefore, we moved to the third iteration, where we took another step back and tried to see through the functional exchange chains. So these colored lines that you can see again, which we call functional chains in Capella, these functional chains actually helped us understand if we have actually and truly modeled every step of a process that would happen in real life. And the difference between the previous diagram and this diagram is that you can see much more functions defined in this diagram here. And that was through the help of the functional chains that helped us realize that we missed out on some functions, which takes us to one of the advantages of this layer is that if we were not able to identify this, we would have realized this in probably the assembly phase or integration phase, which would have been too late to realize an error like that. So the fact that we were able to catch missing gaps in our system very early on in our project meant that we were able to minimize some of the errors and make sure that our costs were within budget towards the end of the project. So here we can see a well-detailed, defined logical architecture. You can note that some of the operational actors that we had at the start of the Arcadia phase are still carried through to this layer of the project, from operators to base station system to the rover system. And within each of these actors, now we've correctly identified our subsystems who are logical components. And within those logical components, we have their specific functions that they will perform. And these functional chains, if you go from the left to right, will take you through a process, almost like going from point A to point B in our system, correctly showing you what functions need to be done to accomplish that process and what events trigger or what functional exchange links those functions. So this is our final version, a third iteration of in our current project for logical architecture with revised functions. And that then takes us to our next layer, our physical architecture, which is where we define how the system will be developed and built to satisfy these logical functions and components. And you can see our physical architecture here. It is a very complex diagram and it's not very clear in terms of what we have. But my purpose of showing this is that, one, to show the traceability within Capella. One of our biggest advantages of using Capella is traceability. The fact that we can link logical components modeled in the previous layer and transition that through to the physical layer. We have identified some of the physical components that we need to satisfy these functions in real life. But not only have we identified those physical components, but we were also able to map those physical components with the logical functions. So now when I present this to my team, not only do they understand what components we have in our entire system, they also understand what functions those components will perform and what they are responsible for. In addition, all these lines that are connecting these functions and physical components have some logical exchange or physical exchange. So either could be a data, command, signal type of exchange, or an exchange that is physical, as simple as wired. So this gave us, our team, a complete understanding of what our solution system is going to look like before even getting to fabrication, before going into manufacturing, assembly and integration. And again, on the point of traceability, you can note that everything that we modeled up to the previous stage of logical architecture was completely transitioned into this layer, and that is one of our biggest benefits here. So having gone through the 4 phases, we also have 2 more diagrams that I want to go through, and these were 2 features that we have in Capella, which these are not Capella diagrams, but these are features available in Capella that I was not able to implement just yet due to just learning the software itself. But from some of the feedback from my mentors and academics, I've had this vision of a modes machine and what it should look like, and I just wanted to get it out there, and this is one of the examples. So a modes machine, our approach to a modes machine is to have one general modes machine, which contains all the general modes programmed onto our computer. And then on top of that, we have subsystem specific modes machine, which expand on the general modes machine. So the idea is that every modes machine we have across the rover subsystems will look the same, except the main operation you see on the left of the blue box over there, main operation, the blue mode, will be expanded specific to whatever subsystem we want to model. So the general one will have common modes like launching, systems check that we always do when booting the system, safe mode, lock, unlock mode, transmission mode, watchdog mode, which is our health maintenance mode. So on top of that, when we move to the diagram on the right, which is a drivetrain subsystem specific modes machine, which is responsible for moving the rover along on the terrain, it now you can notice that the main operation is now expanded, and now it has some subsystem specific modes like linear drive, going forward, back, left, right, steering drive, and it also has its manual mode, autonomous mode. So similarly, we were able to replicate this for all of our subsystems that you saw in the previous logical architecture that we identified over here, like our power supply distribution subsystem, computer subsystem, sensing subsystem. Each of these have their own unique modes machine, which is an expansion of the general modes machine. So moving on to our final diagram is till date, one of the diagram segments of Capella that we spent the most amount of time on and also got the most benefit from, exchange scenario diagram. As a team, we held a lot of mission planning meetings where all of the subsystems would come together. So the moment we finished our logical architecture, the moment we knew what functions every subsystem would have, we then had all of the subsystem members come in to sit in one room, and we just sat and discussed in every minute detail how our rover system would perform on the day of the competition. So we knew what task it had to do. So we sat down and discussed what operation has to happen in that particular sequence for certain scenarios, in certain scenarios, for us to successfully complete certain tasks. And this is one of our examples of one of our exchange scenario diagram, which shows vertically it has all the subsystems, and then horizontally it shows a sequence of what functions need to take place under which subsystem for certain tasks to be completed. For example, the blue sequence you see is our system boot scenario, which goes, okay, when our rover is placed on the lander, for us as a team, what is the process? How do we start? When we boot the system, which subsystem switch on? Do we need all the subsystems to switch on? Okay, if not, which particular? And are we programming this in the computer to know that, okay, only the sensing subsystem and only the drivetrain subsystem switch on when booting? That's for example. And then when the rover performs a particular task and moves on to the next one, are the same subsystems still remain on, or do we need new ones, and can we switch on some else to save power, battery? So these sort of discussions greatly helped us, one, build the right system, two, to optimize so that we can have an efficient operation on the day of the competition. For another example, we have a rover drive scenario. So that is a simple scenario of a rover wanting to go from point A to point B on our lunar terrain. So here we not only just mapped what sort of steering or what sort of linear movement we will encounter, we also accounted for any obstacles we will come in the way, and how will we account for that. If the obstacles come in, is the system able to identify that and overcome? Will it request for any manual input from the user from the base station? All of these were considered. Even actually, to say in simple terms, we considered sunny day scenarios, which is imagining when everything goes right, And we also modeled what we call rainy day scenarios, imagining when something doesn't go right. Say we send a message from the base station to the rover and it doesn't respond on time. Do we keep spamming some key until it responds? But if we do that, will the rover computer receive all this and just get blocked? Or will it have a buffer time where it processes an information, and if it fails to respond, then it sends an information back to the base station, letting our operators know that your previous message was not responded due to this reason. So we can sort of check and rectify those issues without facing any critical issues on the day of operation. So our exchange scenario diagram was something that we benefited greatly, like I said, mentioned before. Not only did it help us discuss and model our scenarios, but through modeling, it helped us identify some gaps. We would model some functions and we would think, hold on, wait a minute, we're going from this step to this step, but there's something missing in between. Shouldn't this happen in this stage? Then we realize that and we go back and add that function to our step. So it was a great step in our Arcadia method and in our Capella software that helped us identify some gaps when modeling the processes. And it saved us a lot of time in our assembly, integration, and testing phase, because when we got to that phase, we realized that some of the errors that would have happened otherwise were already thought of previously and were already designed towards. So when we got to the AIT phase, it was much smoother than we would have otherwise had. So upon completing that, bringing us to conclusion. So we saw all 4 phases in our Arcadia method, from operational, which identified our user goals, to system architecture, which defined our system functions first, logical architecture, again identified logical functions and showed our subsystem interaction, then brought us to our final physical architecture, which showed all our components that satisfy the logical functions. Modes machine defined the modes available in our onboard computers and what events trigger these modes. And exchange scenarios, of course, we recently saw helped visualize the order of operation that we would be doing with relative to time on the day of the competition. So this procedure, we just showed it for the post-landing task only, just to make sure it is easy to communicate this. But this procedure is easily replicated for all the other tasks, and you can imagine how complicated the model become. But it helps us get a very high level understanding of how everything functions, not just for me as a systems engineer, not just for my team, but for the larger team who work in a particular subsystem, but oftentimes won't have much understanding of what the other subsystems are doing or how that fit into the entire project. So this way, we were able to give them a big picture. Moving on, some of our future work. So as you noticed, our modes machine and exchange scenarios were not actually Capella models, but rather just a vision that I had in my head. I wanted to get out and visualize. It was using another platform. So we would like to definitely implement and integrate those models into Capella and integrate that with the rest of the models, so the traceability continues. And we also want to eventually integrate our project requirements within our models in Capella, so that we're able to validate every step of the functions, every step of the way, the functions that we define and develop. And it also adds on to the traceability. So we were in a phase where we were parallelly starting our project and also learning Capella and MBS, getting introduced to MBS at the same time, where we sort of started from operation analysis itself, but eventually our goal for our next iteration of the project is to implement these requirements as well, which will be a great way to map the functions that we define with the requirements, strengthening our traceability. And you just heard from 2 student teams that have implemented MBSE in their projects, 2 student teams that are very new to MBSE, probably their first and second years of experiencing MBSE. But there are many student teams out there who are still in that document-based style, document-based system engineering approach. And if any of you in the audience are associated with any student teams or know any student teams that are keen to try but are on the fence of deciding, having done this for a year or 2, we have some recommendations and best practices. Is that we would definitely recommend assigning a systems engineering specific subsystem within the team that is dedicated and committed to learning MBSE and MBSE practices, and also introduce training very early on in the project life cycle. So through workshops and training, we could have any industry experts that come and help if that's possible, or even members in the university or larger industry that have experienced MBSE and the softwares Capella, softwares like Capella. So it's very important to introduce some workshops at the start of the project lifecycle so that when we come to mission planning and preparation, they are ready to implement that for the project. There are plenty of tutorials that can be followed in these workshops, and of course, once a team is progressed well enough and is confident with their models, I think it's a great practice to have templates for certain teams. That, let's say, a team is revising their project annually, like us. Australian Rover Challenge is an annual competition. It's something that we revise our rover annually. So once we go on to the 2026 competition, our 2027 effort would be built upon our 2026 efforts. So it's very important, and I think it's a good practice to create modeling templates that the future teams can use and build upon. That was developed by past team members. And it can also be adapted for other projects. Now, we are a rover project, but our templates could possibly be used for a drone project that is developed for the same purpose. So these are some of our best practices. Thank you very much to all those who attended today. Thank you for your attention. Thanks for your time. I'd like to have some special mention, one to Mr. Tim Carter, who is one of our biggest mentors in the MBSE field. Everything that we have today is through his feedback from day one. He's been a biggest support, and his way of teaching is very unique, and it has helped us truly learn and understand MBSE in his view. And so I'd like to thank him. I'd like to thank Ms. Kaylee Lee, who's our project lead, who introduced MBSE to SIRI. We wouldn't even be aware of MBSE if not for her bringing in MBSE into the project. And of course, our systems engineering team at SIRI from past. I was not the first lead at SIRI, so I would like to thank our founding lead of systems engineering team who set the foundation for this project, which I was able to take up and build upon. So I would like to thank the members of the past and present who contributed to this project. And thank you all for listening. Thanks for your time.
All right, thank you very much. Yeah, so we have time for some questions. We have a lot of questions in the chat, so I will start with the first one. Is modes machine the state machine based diagram that you mentioned?
Yeah, correct. It's a modes and states machine in Capella. That's correct.
Did you use the model to carry out trade studies for which technologies or solutions to choose? And if yes, how did you go about doing this?
Yeah, trade studies is, I think, one of the another benefits of Capella, which we didn't get to experiencing yet, and it's one of our plans of the future. Because the project was being developed parallelly and we were learning Capella and MBSE at the same time, it was we focused on primarily on the high level of the 4 stages. So really defining functions and functional exchanges and being able to model functional chains and understanding that. But I've heard about and I've learned trade studies through Capella, which I think will benefit greatly from in our future iterations.
Yeah, for sure. And then by using MBSE and Capella, it does help us identifying risk and then potential risk too, so we can mitigate from an early stage.
Okay, so thank you. Will you consider model simulation and model-based testing?
Yeah, definitely. So because we didn't quite get to that in terms of our speed in developing our models. We couldn't really use model-based testing this time of the iteration, but our goal is to eventually have our testings all integrated into our models so that we can verify and validate within the software itself, within Capella itself. So once we develop the physical architecture and once we know a set of tests that we need to perform to verify and validate the system, our goal is to integrate both and see how we can benefit from that.
Okay, that's great. Thank you. Yeah, so it would be nice to know what resources you use, what standards. So you mentioned that the mentoring session with Team, the online resources for Capella.
For sure. Yeah, Team has been very helpful, and of course, everyone at OBO. So we want to take this as an opportunity to give a big shout out to OBO for all the support Romain and the team have given us, and all the sessions, the online sessions we have done, and all the resources they have shared. And also, I have also reached out to my friends and colleagues. They're based in Toulouse. They work for Airbus. They also do use MBSE from Capella. So they have also given us some tips and advice as well. So reaching out to people you know, and of course reaching out to Supaero really helps. Yeah.
Thank you very much, and have a good day. Bye.
Thank you so much. Yeah.
Thank you. Bye.
Bye.